All right, so let's continue with problem H. I think H would be a good one for you to try on your own if you are pretty close to following those previous examples. Because here you do have something close to the derivative of the denominator, but you don't quite have the derivative of the denominator. So this one would be a good one to practice the technique that we saw in the last video. So here I'm looking for an inside function. It looks like I'm dividing by this expression and its derivative or something like it is sitting around on the outside. So I'm probably going to take u to be x squared minus 9. Maybe this would be a good time to mention that it's not necessarily true that there's only one u substitution that would work in a given problem. So it's possible that someone else might choose u to be x squared rather than x squared minus 9. And that would be workable. So it's possible that there's more than one u substitution that will get you to the final answer. However, there's usually a u substitution that will make things especially easy on you. And in this case, it's best to just take the entire denominator to be your u, because then whenever you plug in this expression in place of x squared minus 9, you'll just get division by u rather than a more complicated denominator. So this will be a nice u substitution. And then du would correspondingly be 2x dx. So what we can do now is we can solve for dx in this bottom equation if we'd like to. So you can rewrite this bottom equation as a du divided by 2x is equal to dx, if you just divide both sides by 2x. It would also be okay to just divide both sides by 2 and get that du over 2 is equal to x dx. Both of those are true. And then you could take this x dx, which we have in the original equation, and replace it with a du over 2. So that would be fine, but I'm probably just going to stick to isolating dx and then replacing that dx in the original integral with this expression. So if we do that, what we'll get for our integral is, notice in the denominator, I have x squared minus 9, which is u. So I'll get an x over u, and then the dx I'll replace with this. So the dx will become a du over 2x. And now the goal is to simplify this in such a way that I get an integral that only involves u. So this would, I can cancel the x's here, and this would become an integral of du over 2u, if you want to write it that way. And now I can factor out the 1/2 if I want to, because that's just a constant multiple. So this would give us a 1/2 times the integral of du over u, or if you'd like, you can rewrite that as 1/2 times the integral of 1 over u du. We know that that integrates to an ln of u. So I would get 1/2 times ln u plus c, because we just took an antiderivative. And now as my last step, I just need to replace that u with its expression in terms of x. So as my final answer, I would get 1/2 times ln of x squared plus 9, sorry, x squared minus 9, plus a c. And for all of these problems, if you'd like, or if you're worried about them, you can check your answer by just taking a derivative of what you get here, and you should recover the original integrand. So if I take a derivative of this, I should end up getting this. Because integration was supposed to undo the differentiation. If we want to get back to the integrand, we would just take a derivative. Okay, so let's try problem I here. I is going to be similar. So again, we're looking for an inside function whose derivative or something like it is sitting around on the outside. So here I have an inside function, and something similar to its derivative is outside. So notice that the derivative of this underlined thing would be 3t squared. I don't have a 3t squared on the outside, but I do have some multiple of it. I have a 5t squared. So that'll be close enough. So I'm going to let u equal this inside function, t cubed plus 4. And it's usually a good idea to let u equal the biggest thing that you can on the inside of your function. So if I have this entire expression being raised to the negative second exponent, then it would be a good idea to let this entire thing equal u rather than just letting u equal t cubed, for example. Both of those would be workable, but the thing that's going to most simplify your integral will be to let u be as big an expression as possible on the inside here. So if u is equal to t cubed plus 4, then that means that du is equal to 3t squared dt. And if we want to continue this process of isolating a dt so that we can replace that dt from the original integral, then what I would do is divide both sides from this bottom line by 3t squared. So this would tell you that du divided by 3t squared is equal to dt. So that's just rearranging the line above. And now that will allow us to start replacing the things in this integral with u's. So this would become the integral of 5t squared I can't quite write in terms of u, so I'm just going to leave it for now. But the thing in parentheses I can replace with a u. And then I have a dt out here. The dt I can replace with a du over 3t squared. So that dt is going to become a du over 3t squared. And remember my goal, whoops, this was a 5t squared. My goal is to rewrite this all in terms of just u's. So notice that here I have a t squared in the numerator and a t squared in the denominator. So after canceling, I would get the integral of 5 u to the negative 2 du. And now I've gotten rid of all of the other variable and I just have the variable u. So I should be able to integrate this. To integrate this, I want to apply the power rule. So I'm going to first factor out that 5, put it on the outside of the integral, and then I'm integrating u to the negative 2 du. When you integrate a power of u, you should add 1 to the power, so this would become a u to the negative 1, and then you divide by the new power. So you would get that plus a c. That's the same thing as a negative 5 over u, if you wanted to clean it up a little bit. And then as your last step, you can replace the u with its expression in terms of t. So this would be a negative 5 divided by a t cubed plus 4. And then we still have that plus c sitting around. So that'll give you your antiderivative there. All right, so for this last problem, before we get to the word problem, I want to show you one more application of u substitutions. And here, the idea is that we might not be able to necessarily completely clean up the integral in a single step, but we can maybe clean up an inside function. So notice that in the previous problem, what we had was we had this complicated inside function, and it was to our advantage to replace that with a simpler function, which was just u. So that entire inside function, the t cubed plus 4, we replaced with a u, and that cleaned up the integral a lot. Now we're going to do the same thing down here in problem J. The idea is that if I have a complicated inside function, it might be good to just do a u substitution anyway, even if we can't necessarily clean up the entire integral all at once. So I'll show you how we can do that. So I have this inside function, x plus 1. I would, rather than having a square root of x plus 1, I would prefer something like the square root of u, because we know how to integrate something like the square root of a variable. So I'm going to let u equal that inside function. And in this case, du and dx are nice and simple. So du would just equal dx, because the derivative of that right-hand side would just be 1. So what we would get is, we would get the corresponding integral, the integral of x times the square root of u du, if I just replace that inside with u and replace dx with du. But now we have a slight problem, which is that we have this x on the outside. So I would like to rewrite that in terms of u. Now, in this case, this bottom equation is not going to help us because there aren't any x's in that equation. However, this top equation we can use to rewrite x in terms of u. So if I take that top equation, I can rewrite it as u minus 1 is equal to x. In other words, I can solve for x there. And that will allow me to replace this x in the integral with a u minus 1. So this integral would become the integral of u minus 1 would take the place of x, and then times the square root of u du. And this would be the integral of u minus 1 times u to the 1/2, if you wanted to write it as a fractional exponent there. And then if I multiply, remember that whenever you multiply things like this, you would need to FOIL. And if you multiply 2 powers of u, you should be adding the exponents. So this would give you the integral of u to the 3/2, because that's 1 plus 1/2, and then minus the integral of u to the 1/2. So we're integrating all of that with respect to u. And to do that, we'll split into 2 different integrals. So I want to integrate u to the 3/2 du minus the integral of u to the 1/2 du. Sorry, I'm sort of running out of space here, so I'll try to make this compact. Okay, so now we can apply the power rule to both of these. So remember, we add 1 to the power and we divide by the new power. So if I add 1 to 3/2, it would become a 5/2, and then I should divide by a 5/2. And then I'm subtracting the second integral. This second integral, whenever I integrate, I should add 1 to the power, so it should become a 3/2, and I should divide by the new power. And then I'll get a plus c. And now we're done taking the antiderivative. The only thing remaining is just to replace those u's with their original expression in terms of x, which is an x plus 1. So this would give us a final answer of x plus 1 to the 5/2 divided by 5/2 minus x plus 1 to the 3/2 divided by a 3/2, and then plus a c. Now you could clean up this expression a little bit. I'm not going to worry about it. The main thing is that I just want us to be correctly taking the antiderivatives here. So now we have taken the antiderivative, and the reason that we could do this was because we looked at that inside function and we replaced it with something a little bit nicer by using this u substitution. So we substituted u for the inside, and then we were able to rewrite this as an integral in terms of u that we did know how to compute. So that's the end of the ordinary u substitution problems. In our last video, in the next video, we'll look at the word problem.